Hello everyone, it's Benny, and in this video we're going to be implementing FXAA in an actual 3D game engine. And yeah, you can download the source code of the engine both before and after we implement FXAA in the description, and the build instructions are in the README file. So, before we actually get into the heart of it and start implementing FXAA, I've set up a little comparison for us. You see, with all of the fancy effects we've done with our engine, and a little nudging from a unoptimized terrain mesh, our engine actually dips below 60 FPS, at least while I'm running my screen recording program. So, I've changed our FPS counter to a milliseconds per frame measurement. And this will be sort of our performance measurement for comparing the performance of multi-sample anti-aliasing to FXAA, because, well, one of the benefits of FXAA is it's supposed to be a lot faster. So with multi-sample anti-aliasing in this scene, it's taking us roughly 23 to 25 milliseconds per frame. And there, so that'll be our baseline performance comparison. And as a visual comparison, this is what the scene looks like using MSAA. So it looks something like this. So we have our visual and our performance baseline comparison, just to see what the quality of FXAA really is. And yeah, so now that we've got that out of the way, let's go ahead and let's start implementing, FXAA. So, the first thing we're going to do is we're going to disable multi-sample anti-aliasing. We're not going to need it if we're using FXAA. So in windows.cpp, I'm going to comment out the two lines which allocate space for multi-sample buffers. And in rendering.cpp, I'm going to scroll up to our constructor, and I'm going to comment out the lines that enables multi-sampling. So now if I build and run, you notice that we don't have, our lines are no longer anti-aliased. We have no anti-aliasing enabled. You'll also notice there's no shadows. That's because I disabled shadows off-screen just so I have a slightly smoother recording experience. That doesn't affect you at all. You can leave them enabled. That's just me personally thing. So yeah. So cool. Now we're back to no anti-aliasing. Now, FXAA acts as a filter. And that means we're going to need some way of taking our semi-final image and then basically reading out all the pixels and then applying the filter to them. So that means we can't be rendering directly to the window anymore like we've been doing. Why? Because we would render directly to the window, well, we can't read the pixels back out of the window. So, or at least our engine doesn't have a way set up to do that. So instead, I'm going to create a new texture in my rendering engine constructor. Right below where I initialize the light matrix, I'm going to set a texture. And yeah, I'm going to set a texture. And it's going to be called display texture. So this is going to be the texture we render to for our display. And it's eventually going to be moved to the window. And it's going to be initialized to a new just a regular texture, not with new. And the size will be window get width and window get height. And other than that, it's showing me the wrong constructor, but we're not going to pass in any data, so we're just going to pass in null. It's going to be a texture 2D, because it's a 2D texture. For filtering, we're just going to use GL nearest filtering. We don't care about any fancy filtering or mid-mapping because all the pixels map perfectly to the window. And after that, format, we want RGBA for both of them, so GL RGBA. Clamping, it really doesn't matter, so I'm just going to put false. And finally, we're going to want color attachment 0, because this is we're going to be rendering to this texture. And there, so now we have a display texture. And all is good in the world. So, what I'm going to do is I'm going to change my rendering engine's render function a bit. Everywhere where I used to be using window bind as render target, I'm going to use get texture, display texture, arrow, bind as render target. So now we'll be doing all the rendering we used to be doing in the window. Here's another place, by the way. We're going to be doing all the rendering we used to be doing in the window in the display texture. So at this point, at this point, we've rendered our whole scene into the window. All we have to do now is, well, really just take what's in the display texture, apply FXAA, and move it to the window. So I'm going to use the apply filter function, and just for the time being, I'm going to use mFilter null, which, at least I believe that's what it's called. Oh, it's mNull filter, excuse me. For the source texture, I'm going to get my display texture, so copying from the display texture, I'm going to pass in just null as the destination texture. Or at least I should be able to, unless I have somehow screwed something up. Okay. I think I might have screwed that up somehow. Because I shouldn't... Yeah. Oh. And that's not a pointer anymore. So, don't use the arrow. And apparently I did some refactoring off-screen that's... may have screwed something up. Yeah, thought so. Because now we can't pass in null, and that's necessary for our whole thing. So I'm just going to really quickly change our apply filter so it takes in a const texture pointer for the destination. And that's going to make that work, and it's going to require refactoring things a little bit, but that's okay. So, yeah, I'm just going to build and see what errors come up, because it shouldn't accept things just off the bat. Yeah. So, I'm going to pass address of there. Instead, going to want dest arrow bind as render target. Other than that, I think that's everything. Oh! Is there... Ah. Address of source is not equal to dest. There. Other than that, I do think that's everything. So yeah, now if I build and run... Ah, good. So now we're rendering to the display texture, and now we're properly copying it into the window at the end. We're not actually doing FXAA anymore, but we're still using the null filter. So, in fact, let's go ahead and do that. I'm going to add, in renderingengine.h, I'm going to add a new variable, a new shader. So it's going to be shader, going to space over, and this will be FXAA filter. And this is going to put this under Gauss blur, and it's going to be filter-FXAA. At least that'll be what the file's called. We haven't created it yet, so it's not going to work, but at least it's there. So I have it now, and it should be initialized once we create the file. And there, now we should be applying the FXAA filter to it. But of course, we haven't created that file yet. We haven't written the shader. So our code should be okay, we just need to write that. So let's go ahead and do that. So here I am under the shaders folder. And what I'm going to do here is I'm going to start by copying my null filter. Just as sort of a base. And I'm going to, of course, rename this to filter-FXAA. So there. Now I have the vertex shader and fragment shader. They don't do anything just yet, but they're there. And yeah, now I should be able to build and run this, and everything should work, because now we actually have a shader written. Doesn't do what it's supposed to yet, but that's coming. Alright, so good. We're now copying with the FXAA filter, and all we should have to do now is really write the filter. But there's only one more thing, though. You see, in FXAA, we are going to need to know how big 1 pixel is. So I'm just going to go ahead and do everything that requires modifying the rendering engine first off. So after that, we can just focus on implementing, well, really, the FXAA code in the shader. So I'm going to take in one more uniform. It's going to be uniform vec3. I'm going to call r underscore inverse filter texture size. Yeah. And there. So what I'm going to have to do is I'm going to have to set vector 3f right before I do all this, and it's called inverse filter texture size. And the value for this, well, of course, it's going to be a vector 3f, and it's going to be get texture, display texture, well, 1.0f over that get texture, display texture dot get width, and the second parameter is going to be 1 over get texture, display texture dot get height, and our last parameter is going to be 0 because we don't the two-dimensional texture, so we don't care about the last parameter. So I should be able to build, and it shouldn't run anymore because we're not actually using it, but yeah, at this point we should have all the parameters set up to actually perform FXAA. As I said in the last video, FXAA works in 2 stages. The first stage is detecting if this pixel is part of one of those stair-stepped aliased edges. And the second stage is, if it is part of one of those stair-stepped aliased edges, then blur it in a way that looks like it's anti-aliased. And the first stage of detecting if it's at an edge, there's a lot of ways you can do it. The way I generally recommend, if you don't have a good reason to use another way, is luminosity. So here's a vector right here. This is sort of the luminosity vector. If you multiply a color by this, or do a dot product with this and a color, then it will give you a float of the luminosity of that particular color. And there's some official organization that determines what exactly these values should be, so that's where this comes from. So, as I talked about in the last video, we're going to sample in sort of an X pattern. So we're going to have some floats. One's going to be luminosity in the top left. Whoops, that's not the duplicate key. And we're also going to have 4 more. 1 for top right, 1 for bottom left, and 1 for bottom right. And also 1 for the middle. So the luminosity of the middle pixel. And the way we determine these is generally pretty simple. I'll start with the middle, since that's the easiest to get. It's just whatever pixel we're at right now. So I'm going to take texture 2D of text chord 0.xy, and wait, I'm going to take text 2D of the filter texture, of our underscore filter texture, at text chord 0.xy. And I'm going to get the XYZ, which is the RGB component of it. And as I said, if I do the dot product of this, well, the luminosity, and this, then lo and behold, I now have the luminosity of the pixel. And everything else works very similarly. So in fact, I'm going to copy and paste this as sort of the basis. The difference, of course, is the top left is going to be 1 pixel up and 1 pixel to the left. Well, at least in image space. So the way I'm going to do this is I'm going to take text chord 2D xy plus a vec2. And I'm actually going to do this all in parentheses here. Let me put it this way. We're going to go -1, so that goes to the left. You know, negative goes left. Makes sense. But because of the orientation of texture coordinates, going up does mean going negatively. So yeah, we're going to have to go -1.0 to go up. So yeah, that can be a little tricky, but well, there you go. And now to get this, to make these -1, actually, you know, 1 pixel in size, I'm going to multiply this by R inverse filter, and good lord, that's a long name. So in fact, just for convenience sake, I'm going to make a vec2 here called text chord offset, and that's just going to equal R inverse filter texture size dot xy. There. And we're going to multiply that -1, +1, by the text chord offset. There. And everything else goes through a very, very similar process. So I'm going to copy and paste. And whoops, except for the middle. The middle is fine. Top right goes positive on x, bottom left positive on Y, and bottom right, positive for both of them. So there. Now we have the luminosity of all the pixels and sort of across. And just to sort of show something right now, I'm going to do a float temp value, which is going to be the luminosity of everything, just to show that this is actually working. So I'm going to sum the luminosity of everything really quickly. So bottom left and bottom right, sure, doesn't matter the order. And I'm going to take all that and multiply it times 0.2, so it's an average. And our text color is going to end up being, just temporarily, a vec4 of temp val. And there. So now, this should give us basically a converted image to luminosity component, and it'll make it grayscale. So this is just a text to make sure our code is actually working. So yeah, everything is black and white, and as you can see, well, everything is slightly blurred, and it looks a little bit interesting. So this is what this is what the luminosity part of our image looks like if we blur everything. It's kind of interesting. But of course, that's not what we're here to actually do. We're here to anti-alias the image, not make it black and white and blur it. Now, this next step in the algorithm is a little interesting, because we're going to be determining both the blur direction and whether or not this is, a pixel at an edge or not, the edge detection, all in the same step. So, yeah, this is going to be interesting. I'm going to create a vec2 for the blur direction. And I'm going to set the x of this, so direction.x, based on the luminosity. So I'm going to be determining the direction from the luminosity. And here's how I determine the direction that I blur. First off, I'm going to sum the luminosity in the top left and the top right. Okay, so that's going to give me whatever the sum of them is. Why? You'll see in a moment. I'm also going to take the sum of the luminosity in the bottom left and the luminosity in the bottom right. So now I have the sum of these two things. And what I'm going to do is I'm going to subtract them. I'm going to subtract the luminosity in the bottom left from the luminosity in the top left and top right. And I'm going to do something very similar for direction.y, except rather than, of course, using top left and top right, I'm going to be using top left and bottom left minus top right and, well, minus top right plus bottom right. And that's going to be the y. And you might be wondering, well, what on earth is all this nonsense? How is this determining a direction? Let me show you. So when we sample a point at an edge, we'll get luminosity values something like this. So the top left is this sort of gray color, and the top right is this darker color. Now we sum them, we get a value. Now we sum the bottom left and bottom right, we get the same value since these are the same color. So in this case, we're not going to be blurring on X at all. But for Y, we take the sum of the two left. That'll be the sum of these two gray colors. And we take the sum of the right. That'll be these two darker colors. And if we take the difference of that, then that is a significant value. So we will have some amount of blurring on the y-axis. And as you see, if we look on the y-axis, above it, there's not in the triangle, and below it there's in the area. So it works. And it's a little interesting the way that works, but yeah, this is how we're determining at least the direction. One thing you do have to be careful of is, because of the texture coordinates, one direction is inverted, top is down, direction.x will need to be inverted because of that. Otherwise, our x direction, it'll be inverted. That doesn't matter too much right now, since the actual value doesn't matter. At least at this point, we're going to have to do some adjustments. But it will matter for when we do all that. So now, the value's wrong, but it's pointing in the right direction, and that's exactly what we're going for. And you might be wondering, well, this gives us the blur direction, but how on earth is this determining if how's this doing edge detection? And here's how. What if all these values were the same gray color? Well, I do all the math, do the subtraction, and I get 0 on x and 0 on y. That means whatever blurring I do, if I'm going 0 pixels away, even after the adjustment, 0 pixels away is sampling the same pixel. So whatever blurring algorithm I apply to the exact same pixel, it's going to end up giving me the exact same pixel I put in. So therefore, if this isn't at an edge, it won't perform any blurring, because there won't be any magnitude to the blurring direction. I know this is a little bit interesting concept. It's a little... it's definitely not the way you'd think of doing edge detection at first. But it works, and it works pretty well. So hopefully that makes some sense. Okay, so at this stage of the equation, we have a blurring direction. And the direction part of that is correct. We know what direction to blur in. The problem is, we don't know how far to blur in. We don't have the proper magnitude of this. And there isn't an especially good way to determine this. So we're going to have to do a little bit of fudging. And the first off the thing is, what we're going to do is we're going to do sort of a way of normalizing this. It's not really normalizing, but what we're going to do is we're going to scale this vector up so that whatever the smallest component is becomes the length of 1. So if our direction.x is the smallest, that's going to be scaled up until that's the size of 1 pixel. And we can get a float that does that pretty easily. I don't know what to call it, so I'm just going to call it temp for now. I'll think of a name in a moment. And all we have to do is say 1 over, and I want the minimum of the absolute value of direction.x and the absolute value of direction.y. Okay, so this will take... it's only paying attention to the magnitude, so that's why the absolute value, and it's taking the minimum of it. And now we can do... now we're doing 1 over that. And that's great. So if I multiply my direction by this temp variable, if I say direction equals direction times temp, then what do you know? It's now been sort of had that modified, not really normalization thing, where it's scaled up so whatever the smallest component is has a length of 1. Now, of course, the one obvious problem with this is, well, what happens if direction.x, for instance, is 0? Then we have a problem. So we're going to need some sort of reduction to this value. So I'm going to have some float. I'm going to call it direction reduce. So, yeah, and this is basically so that, well, we don't divide by 0. And you can just hardcode this as 128.0. And that works. So I can say that, and I can just do whatever this value is plus my reduction amount. And this way, this way we won't have a divide by 0, and that's nice. But that's only solved one problem. Another problem is, if we just scale this up to whatever, we can get a really, really long direction. I mean, we get a direction that spans hundreds and hundreds of pixels, so that's not what we want. So what we can do is we can sort of clamp this. I'm going to go to the top, and I'm going to have some float FXAA underscore span max. And I'm going to set that to 8.0. And this way we can just, well, now we can just do sort of a basic clamp. I can take a vec2 of FXAA span max, and just basically both of those components. And I'm also going to have another vector2, which don't have the right syntax for yet, but in a moment, of that. And I want to take the maximum of the direction.temp and this, so this way it's above -8, -8. And I'm going to take the minimum of whatever that is and that. And that's just going to clamp it. And actually, now that I think about it, I probably could use the clamp function for this, couldn't I? Oh well, I'll leave it like this for the time being, and I'll see if I really can use the clamp function. But yeah. Okay. So now we've got it scaled up, so it's a reasonable amount, and we have it clamped so it doesn't go ridiculously far away, and we're also reducing it by some amount so that, well, so that it doesn't divide by 0. One final degree of control we can sort of give over this is we can bias the amount we reduce it by, based on the average luminosity. And that's a complete and total hack, but it just makes it slightly, well, it gives you slightly more control over how the direction is reduced, and that can give you slightly different forms of aliasing. So, first off, I'm going to create 2 more variables. One's going to be FXAA reduce min, and that's going to equal the 1.0 over 128.0 I have right now. And I'm going to have one final float that I'm going to be calling FXAA reduce mul. And I'm going to set this to 1 over 8. And this is sort of the bias amount for this. So, anyways, what I'm going to do is I'm going to alter my direction reduce amount. And, of course, this is an average. So I'm going to take my top left, in fact I'm just going to copy this as a start, my top left and top right, plus my bottom left and bottom right. Sure. And I can multiply that by 0.25, and hey, I've got an average. But of course, I'm going to multiply this again by the reduce mul, because that's sort of the bias amount. So there. So that's going to be sort of our base amount of reduction. And just to make sure this, again, doesn't end up being 0, I'm going to do the minimum of this and the FXAA, well, reduce min. So this way, it just gives us a slightly nicer way of reducing, well, yeah, reducing the direction. And you can, I'm eventually going to make these uniform, so you can just play endlessly with what these values should be to make it look best for whatever you're doing, but yeah, for now, again, don't freak out too much about why is it done this way. This is, again, this is all really just a big, gigantic hack. And I'm going to just say, call this inverse direction, I don't know, inverse direction adjustment. Sure. And there. So now we should have the direction basically properly adjusted. So now we know we have the proper blur direction and our completely hacked proper blur amount, or magnitude, I should say. So yeah, so with all that out of the way, all we have to do now is actually perform the blur and assign that as a fragment color, and we're done. So, yeah. Okay, so to perform the blur, first off, I'm going to take this direction that we have, and I'm going to transform it into texel space. So the way I do that is just like I did with these over here. I'm going to multiply it by text coord offset. So now, if I add direction, it'll give me some number of texels, essentially. And there. So now I'm going to create a float, result 1. Why result 1? You'll see in a moment. But for now, it's result 1. And what I'm going to do is I'm going to take 2 samples, one on both sides of the direction, essentially. So I'm going to take 1/2 to average them. I'm going to multiply that by something very similar to what I've done with the luminosity thing up here. So I'm going to, in fact, copy that. And I'm going to be sampling the filter texture with my direction as well as the amount. And what I'm going to do is I'm going to multiply that. Bear with me for a moment. I'm going to multiply that by some vector 2. So I'm not just going to go full out in the direction. I'm going to sort of scale it down by some bit. And in this case, I'm going to scale it down by 1/3 plus 0.5. So, wait. Yeah, I think I'm doing that backwards. Sorry, 1/3 minus 0.5. So this will give me some amount backwards on the direction. And I'm going to add that to another sample, which is 2/3 minus 0.5. So I'm going, 1/6 along the direction, both forwards and backwards. So I'm taking, again, one sample on both sides. And you might be wondering, why 1/6? Because with result 2, I'm going to be doing the rest of the samples. So result 2, by the way, this is just one way you can perform the blur. You can do the blur with just about anything you want, but this way tends to work fairly well. It's not perfect, but it works fairly well. Now result 2 is going to be very similar. In fact, I'm just going to copy everything that I had in result 1. The key difference is I'm going to be doing 0/3 and 3/3. So this time I'm going full all the way. Now the only thing left to do is I need to mix result 1 and result 2. And the way I'm going to do that is I'm going to take result 1, and I'm going to multiply that by 1/2 again, and then I'm going to add all this times 1/4. So this way each sample gets 1/4 weight. So there. And the reason I've split it up into two results like this is because I'm going to perform a test. I'm going to get float result 2, well, I'll call it Luma result 2, just to stay consistent. And guess what? That's going to be the dot product of the luminosity and result 2. Essentially, this is going to be a way to test if I've sampled too far. So if my result 2's luminosity is outside the range of all these other luminosities, then clearly I've sampled too far, and therefore I'm going to use result 1, which is much, much tighter range, only 1/6. So, yeah. And that's the way that's going to work. So in fact, while I'm at it, I can delete all this code. And, and I don't have averages yet, so I'm going to have some float called luma min. Actually going to do this above result 2. And this is going to be, well, as you can probably imagine, I'm going to take the minimum of all the luminosities. So min of luma m and luma tl and luma tr, and the minimum of, everything. Luma bl and luma br. There. So that should give me the absolute minimum luminosity of all the pixels I sampled. And I'm going to do the same thing for max to get a maximum luminosity. So this will be luma max. And there, so now I have minimum and maximum, and now I can successfully test if luma result 2 is in range. So if luma result 2 is less than luma min, or luma result 2 is greater than luma max, therefore it's outside the luminosity range and it's going to look really weird. So if this is the case, then my GL frag color is going to be a vec4 of, and result 1 and result 2, those should be vec3s. We're sampling color data, so yeah. If that's true, then I'm not going to use result 2, because result 2 is out of range, and I'm going to use result 1. So vec4 of result 1, and 1.0 for alpha. Otherwise, it's safe to use, and I can say the frag color is result 2. And that just about does it, folks. At this point, we now have FXAA. And if I run my engine. Okay, I've made a few mistakes. So, one moment. I'm just going to fix all the errors off. Oh, well, that's just a missing brace. I don't need to do that off screen, I don't think. Well, okay, the brace should be there. And now, okay. And as it turns out, I've made a couple of typos. For one, in LumaMin and LumaMax, well, I forgot one extra min and max around the two, well, existing min and maxes, if that makes any sense. So, do like that, and it's fixed. Another issue is with direction reduce. I'm doing the minimum of some value and the minimum. Yeah, that's not supposed to happen. I should be taking the maximum. See, maximum of this luminosity calculation and the minimum. There. And finally, in inverse direction amount, I'm doing the min of absolute value of direction.x and absolute value of direction.x. Yeah, that should be absolute value of direction.x and absolute value of direction.y. There. Much better. So, once all that is done, I should be able to build and run, and look, our scene now has FXAA applied to it. And, well, yeah, the parameters might not be perfect right now. It does add a little bit of fuzz. I think the parameters might need a little bit of adjustment, but hey, you know what? It is working. So, final thing I'd like to do is I'd like to take these FXAA, span, reduce, all these parameters, basically. And I'm going to make them uniforms, so that way we can specify them from the rendering engine. And we can even adjust them dynamically if we really want to, for whatever reason. So I'm going to take in a uniform float R FXAA a span max. There. That's how I'm going to do it. So, yeah, and then I'm going to have FXAA reduce min and FXAA reduce mul. Okay, so I went ahead and refactored the code off screen. So I replaced all the constants with the new render variables things. So, yeah. And now all I have to do is go to the rendering engine and set some floats. So, yeah, in fact, I'll do that right here. I'm going to set a float called FXAA span max, for instance, and I'll set that to 8.0. And while I'm at it, I'm going to move this up, because otherwise that's going to bother me. For some reason, it seems to me like all the settings should be done in one place. But yeah. So I'm just going to set all the parameters, and you can set these to whatever you want now. And, whoop, that's not where it is. So we need reduce min and reduce mul. That was 1.0, and reduce min was 1.0 over 128. There. So now if I build and run, everything, yeah, should be working just as it was before. And finally, it's time to follow up on that performance comparison. So I'm going to re-enable shadows in the rendering engine. You probably didn't disable these, but I did, so that I could do this comparison. And now we're going to see what the scene looks like with FXAA enabled, and how well it performs compared to multi-sample anti-aliasing. So, well, this is what the scene looks like with FXAA enabled. Actually, the angle's a little bit more like this. Yeah, from about the same viewing angle. And as you see, now the scene's only taking, about 20-21 milliseconds to render. So, the whole thing is 4 milliseconds faster just by changing to a new anti-aliasing system. That is a pretty huge performance improvement. But yeah. So, now we've got FXAA enabled, and it makes things look nice and smooth. And perhaps you can adjust the parameters again and get them looking exactly like you want. So yeah, that's how you implement FXAA in a game engine. Only thing I'd like to say before we go is, wherever you happen to apply FXAA, make sure you do it before you do it with... Before you, make sure you apply the filter before you draw your HUD elements or anything like that, because otherwise it'll anti-alias those as well. So yeah, hope you enjoyed, hope you learned, and I'll see you next time. And one more thing that I completely forgot to mention for some reason. Our display texture was previously using nearest filtering, and it produced decent quality anti-aliasing, but there's also some texture speckling. And you can reduce that by playing with some of these parameters, especially FXAA reduce mol. If you play around with those, you can reduce that a lot. But another way that you can handle that, and improve the quality of anti-aliasing, is changing the display texture to linear filtering. If you build and run that, you notice anti-aliasing quality is all of a sudden much, much better. FXAA now is very comparable to the quality you'd get from MSAA, or another geometry-based anti-aliasing technique. So, yeah. Really, the big downside to all of this is one of the biggest causes of the infamous texture blurring issue. Because now, the blurring direction vector, if that's a really small value, meaning no edges detected, that no longer maps everything to the exact same texel. It'll cause some very slight amounts of interpolation among all the other texels, and then, hence, slight texture blurring. So, take your pick. Do you want slight texture blurring and better quality anti-aliasing? Or do you want no texture blurring, some slight texture speckling, and not quite as good quality anti-aliasing? Both of these effects can be helped a lot by playing with some of the settings, but again, take your pick. So, thank you, hope you enjoyed, hope you learned, and now I'll see you next time.